So this is chapter 4.2, problem 28 on page 174. In this chapter we talk about finding the regression equation for the data set, and we're going to show you how to do that. So in this problem, do larger butterflies live longer? The wingspan in millimeters and the lifespan in days were measured for 22 separate species of butterflies. The data set is in the textbook on page 174, and the Excel file is under the data sets under Blackboard. We're going to, in part A, compute the least squares regression line for predicting the lifespan from the wingspan. But note, we're going to show the scatter plot first on Excel. I mean, not on Excel, on the TI-83 and 84. Then on Excel. Is it possible to interpret the y-intercept? Explain. And we will explain that when we get to it. If the wingspans of two butterflies differ by 2 millimeters, by how much would you predict their lifespans to differ? And then finally, in part D, we're going to predict the lifespans for a butterfly whose wingspan is 28.5 millimeters under the equation we found in part A. So the first thing we're going to do is show the scatter plot. So we enter the data L1 and L2 under the stats key. In this case, the X data is the wingspan, and it's called explanatory. The L2 data, which is going to be the Y data, is the lifespan. Once we've entered the data, we're going to press second equal key, and we get the following menu screen. And we choose, in this screen, we make sure that the plot is on. We choose the first icon, which is the scatter plot icon. We get the X list L1 and L2 is the Y list, and we leave the mark alone. Once we finish with this screen and this plot, we press the Windows key, which is the next key to the Y equal key, and we choose our scale. We have, in this particular case, I chose 10 to be the X minimum and X max to be 50, and I did that for both scales. I also set up the scale size to be 2. Then we finally press graph, and here is our scatter plot that we have for our data set, and you can see it is kind of slightly negative. It's kind of really scattered, but it is slightly negative. So now we want to find the regression line in this particular case. And remember, this is going to be our best fit line. Y hat is equal to mx plus b. There's our slope. This is our y-intercept. So once the data has been entered into L1 and L2, again, L1 is our data list, we press the stat key again. We move our cursor over to calculate, and we get this menu screen, and we choose option 4. The book chooses option 8, but that means that we've switched the B and the M's position in the equation. We want to make sure that the diagnostics is on, and that is you have to hit the second key and the 0 key you get catalog on and you go down until you get diagnostics on, and you hit it twice. So in step 3, we press, we make sure that we press L1, L2 for your XY list when we actually enter in linreg. And then we press enter and we get the following screen. And here is our mx plus b. A is our slope in this case, and b is our y-intercept. And of course our correlation, which we've already discussed, is there, and it's a negative 0.412. So in this case, we want to take what our equation is from the last slide. We found the slope to be a negative 0.845 times x, that is our wingspan, plus 52.04, right? And the question is it possible to interpret the y-intercept? Explain. No, the answer, it's not possible to interpret the y-intercept in this case. We note that when the wingspan is 0, so when we put 0 in for x, the butterfly lives on average 52 days. A 0 wingspan does not make sense in this case. Part C says, if the wingspan of two butterflies differ by 2 millimeters, by how much would you predict their lifespans to differ? In this case, we use the slope to find the relative differences. The slope in this case, y equal negative 0.845. So if the butterfly differs by 2 millimeters, then the lifespan would differ about negative 1.69 days, and that is from the lower wingspan to the higher wingspan. And then finally, can we predict the lifespan for a butterfly whose wingspan is 28.5 millimeters? Here we use the equation that we found, and we plug in the 28 where x is, and we get the following result. So we assume for 28.5 millimeters wingspan that the butterfly will live on average 27.96 days. Finally, we did the same problem using Excel. In this case, we entered the data into two columns, in column A and column B. We clicked a cell outside the range of column A and B and moved the cursor to the insert key at the top of the page. Then we selected the scatter diagram icon, and from that we hit enter. We get a blank chart, and we select for the data, the X data, we choose the column A, which is with the wingspans, and the Y data, the B, in the lifespan, and we press OK. At this point, we get a chart without the titles, and we want to put the titles in: wingspan in millimeters and days of lifespan, and butterfly lifespan, the chart title. And we just get the scatter plot primarily. How we get the equation and the line is that we click one of the points inside the chart, and on the side we get a plus icon on the side here, and we click that and we go down to trend line with more options. We select the linear with equations and the R-square. Sometimes we have to click the line itself and get more options from that to get the equations and the r squared. We'll show you how to do this in class this week. So that concludes this problem 4.2. A lot was in here, and we'll discuss it further in class, and then we'll go to chapter 4.3.